We're beginning Unit 3.1, which is navigating the periodic table and understanding the periodic law. The different patterns that we see on the periodic table repeat themselves. The periodic table, you're going to find a very useful and important tool. As a chemist, you're going to use it on every single test because it's going to help us learn a lot of information about chemical bonds and chemical reactions. Dmitri Mendeleev was the father of the periodic table. When he created his periodic table, he looked for patterns. He looked at physical and chemical properties. He looked at things like melting point, boiling point, and he also looked at chemical reactivity and density and phase of matter. So he looked at all sorts of things. And when he saw patterns, he put the elements in columns, vertical columns, based on the way they chemically reacted, and he put them in rows horizontally, with the elements increasing in atomic mass from left to right. Now, there were some problems with his table. There were some elements that were not yet discovered. So he left blank spaces on his table, and as it turns out, he was right. There were elements that had not yet been discovered that belonged on his table. Now, on occasion, he broke the pattern of increasing atomic weight to make sure that the pattern was kept. An example, if you look at the elements on your periodic table, I want you to go to element number 52, which is tellurium, and then I want you to look at element 53, which is iodine. If you look at their average atomic mass, tellurium has an average atomic mass of 127.6. Now I can round that up to 128. If you look at iodine, which is the next element to the right, it only has an atomic mass of 126.9. And that rounds to 127. Based on these atomic mass numbers, the elements should really be in reverse order. Iodine should come before tellurium. But if we look at the pattern, based on their physical and chemical properties, iodine belongs exactly where it is, and tellurium belongs exactly where it is. So Mendeleev just assumed that someone had miscalculated the atomic mass of iodine and tellurium, when in reality what we now know, atomic mass, it's about atomic number. So we now understand that the atomic number is the functional property that we use to categorize the elements on the periodic table. The horizontal rows on our periodic table are called periods, and there are 7 of them. So to the left of the table, you would see periods 1, 2, 3, 4, 5, 6, 7. The vertical columns are numbered 1 through 18, and they're called groups. The periodic law basically states that when the elements are arranged in order of increasing atomic number, we see a periodic repetition of their physical and chemical properties. So, if you look at the example I have below, you see that the properties of lithium repeat with sodium. They're both metals, and they both mark the beginning of their horizontal row. All of these elements here are in period 2. All of these elements here are in period 3. And the patterns repeat themselves. The first element, lithium, the first element, sodium, they're both metals. The second element, beryllium, and the second element, magnesium, they're also metals, and they have more in common with each other than they do with sodium or lithium. So we see that all of these elements that are connected share the same chemical properties. On the periodic table, as I said, the horizontal rows are called periods. And the period numbers correspond to the number of occupied energy levels for the electrons. In other words, it tells us how many rings they have. If you're in period 2, your atom will have 2 rings. So all the elements in period 2 will have 2 electron shells. If you're in period 3, you'll have 3 electron shells. Also, we can notice that there's a pattern with the valence number. So if you look here, the first number, 2, tells us that there's 2 electrons on the first ring and 1 electron on the second ring. That valence number corresponds to the group number. So all of these elements have a valence number of 1 electron. If you're in group 2, your valence number is a 2 all the way down. And if you're in group number 3, your valence number is a 3. If you're in group number 4, your valence number is a 4. Group 5, group 6, group 7, and I don't know why they say 0 here, but this is group 8. They have 8 valence electrons. Now, look carefully at the number here. Period 2, you see 2 digits, that's 2 rings. 2 digits, 2 rings. So the number of digits in the electron configuration corresponds with the number of rings. In period 3, they all have 3 numbers. The groups, which we sometimes call families, so each group that's highlighted here with a color, they have a specific family name, or they have several family characteristics that they share. If they're in the same vertical column, the groups will have similar chemical and physical properties. So all of these elements here that are in red are more like each other than any other element on the table. The elements here in orange, they're part of a family, and they all are chemically similar in their physical and chemical properties. The elements over here in purple, those are our noble gases. They're all chemically unreactive. So each vertical group has chemical and physical properties that they share. When Mendeleev arranged the table, he did that on purpose. Why do they have similar properties? Well, it all comes down to those valence electrons. Remember, I told you we have our left side losers and our right side robbers. So if we put the staircase in there just to show you what's going on, this is where we separate the lefty losers from the right side robbers. So these elements tend to lose their electrons, and these tend to gain. If you're losing electrons, then you're going to form the same kinds of ions. These elements here will all lose 1 electron and become a +1 ion. In the second vertical column, they'll become +2 ions because they're all going to lose 2 electrons. And that pattern continues. If you gain electrons, well, this group will not lose or gain. They won't form an ion. They're chemically unreactive. But this group right here, they'll form a -1 ion because they gain 1. This group will form a -2 ion because they'll gain 2 electrons. And the pattern repeats. Here's another way to organize the information and look at it. The tall columns here, sometimes we give them the group numbers 1. Let me just point to them so that we can follow along. 1, 2. This is really group 13 on your table, but we're saying it's the third tall column. 4, 5, 6, 7, 8. These numbers correspond to the valence numbers. The middle group here in the D block, the elements that we fill the electron shells out of order, they will hold a valence number somewhere between 1 and 2. But the tall columns, they have patterns. All of these will have 3, they'll all have 4, so on and so forth. The families of the periodic table also have names. Now, families can be a single vertical column or they could be several columns together. And these are the names that you should know. So I'm going to take a moment so that you can copy them down. Group number 1, they're called the alkali metals. Group number 2, they're called the alkali earth metals. Groups 3 through 12, this whole block, we call them transition metals. One of the properties that they have in common is when these metals form ions, they form colorful ions. So the blue color you have when you have a copper salt comes from the copper ion. The green color you see with nickel, the yellow color you see with chromium, or the orange color, all of those different colors are a result of the transition metals. Group 13, 14, 15, and 16, they don't have a specific family name. But when we get to group 17, starting with fluorine all the way down to iodine, the first 4 of this group are known as the halogens. And the last group, group 18, they're the noble gases. What they have in common is the entire family of elements are all gases at STP. That's standard temperature and pressure. And they're all chemically inert. That means that they do not react. So their property is to chemically not react with any other elements on the periodic table. Here is a color-coded table where you can see hydrogen really doesn't belong to any family. It's kind of its own element. It's in its own group. But if you look at the rest, the orange here shows the alkali metals, and we've color-coded them in orange. The peach pink color here, the coral, those are the alkaline earth metals. In the middle here, you have the purple. Those are your transition metals. Along the staircase, you might notice that there's a few elements here that are in blue. These elements are known as the metalloids, or the semi-metals. We'll talk more about metalloids in the next chapter. These are elements that have properties of both metals and nonmetals. They're also known as semi-metals. And I want you to notice that they're the elements that are found right along the staircase. In general, we accept that there are 7 metalloids. Boron, silicon, arsenic, tellurium, and New York State Regents considers At to be a metalloid. Germanium, named after Germany, and antimony. Those 7 are the metalloids that New York State Regents would like you to know. And then over here, as I said, these are our halogens. We really don't consider At a halogen. It's really these 4, fluorine, chlorine, bromine, and iodine that we consider our halogens. These are the most reactive non-metal family. And they happen to be diatomic. We'll talk more about that at the end of the unit. I mentioned it when we did particle diagrams. It means you have 2 atoms of the same kind. So when you draw a particle diagram, it's 2 particles of the same kind that are bonded. And the final group over here, these are our noble gases. In the next unit, we're going to look more closely at each of these families and the specific chemical properties they have. Down here on the bottom, there are two other groups. The two rows that were pulled out, you can see that the yellow row begins here. It's really an extension of the horizontal row number 6. This yellow group starts with the element lanthanum. So we call it the lanthanide series. All the elements in the lanthanide series have something in common. These two groups here make up the rare earth metals. So that's one thing that they are known for. They are rare earth metals. And down here, the green family starts with the element AC. That particular group is known as the actinide series. So this group here is lanthanide. This group here is the actinide series. And these elements in particular are artificial. They are not naturally occurring. When I say something is artificial, what I really mean is that it is a man-made element. And at the end of the year, when we talk about nuclear reactions, we will talk about how all of these elements were made by transmutating uranium. And you can see that a lot of them are named after the planets. Uranium is named after the planet Uranus, Neptunium after Neptune, plutonium after Pluto, americium is named after America, berkelium named after Berkeley University, californium after California, einsteinium, fermium is named after Enrico Fermi, and there's mendelevium, named after Dmitry Mendeleev. So a lot of these elements were named to honor different scientists or different universities where they were discovered. So we're going to learn a lot more about the periodic table of elements in the next coming units.